Hi everybody, this is Dr. Bricker here with the review for Exam 2. So Exam 2 does cover Chapter 9, which is on momentum, Chapter 10, which is on energy, and then we go back to Chapter 6, which is circular motion, and Chapter 7, which is rotational motion. So it is 12 questions, similar to the practice test. You do have to show your work. It is multiple choice, but you do have to show your work. If I were going to study for this, I would definitely go over the practice test, go back over the homework problems that we did from those chapters, take a look back at the PowerPoints. If you have time, read the chapters. If you don't have time to completely read the chapters, at least go through the summaries at the end of the chapters. Now when you take the test, if you were, like it was a class where you met in person, I would allow you to make your own formula sheet, like one page, put whatever you want on there. So I think for this, I mean, you're doing it, wherever you're doing it, at home or wherever else you choose to do it. I would also get organized in that way. Have some sort of formula sheet that you make for yourself, because you get 2 hours to do it and take pictures of it, upload it. But be organized. Have all your formulas ready to go, little example problems, whatever you might need. Okay, so let's take a look at the actual test. Okay, so the first one, before anything else, show all work for credit. So you got to show all your work here. You get partial credit that way, as you know from the first test. A car moving steadily at 10 meters per second encounters a highway bump that has a cross-section of 30 meters. Circular cross-section. Okay, so that's a clue that this is a circular motion problem. So let's see, we're traveling at 30 meters per second. The radius of this curve is also 30 meters. The car maintains a steady speed over the bump. Okay, so that's uniform circular motion. What is the normal force exerted by the seat of the car on the passenger? So how much is the normal force? And actually, we've been using little n for normal force. How much is the normal force? And we know the mass of the person is 60 kilograms. Okay, at the top of the bump. Draw the free body diagram. Okay, so here's going over the top of the bump, normal force, and the weight. Now we know in circular motion, if you're going in a circle, there has to be a net force towards the center, so I'm going to actually make this mg bigger, the weight bigger than the normal force, just to really illustrate that point. And then you have a net force towards the center, right? This is bigger than this, so there's a net amount towards the center. Okay, we're going over this at a constant speed. This is Newton's second law. F is equal to ma. It's just when you go in a circle, this is a special kind of a called radial acceleration, along the radius towards the center. And then again, this is the part where you have to fill it in. What are the actual forces? Well, I'm going to put mg minus the normal force. That gives me a net amount towards the center. And then I can solve for the normal force. One other thing, don't forget that radial acceleration is equal to v squared over r. So I'd like to sneak that part in here. M v squared over r. I should have had that in there to begin with. And then here's the actual forces. So it starts like this. F is equal to ma, special kind of a. And then we know radial acceleration is v squared over r. And then we could put the actual forces in. Have to do a little bit of algebra. Normal force then turns out to be mg minus mv squared over r. Okay, so this is the normal force from the seat onto the person. That's the same thing as a normal force from the person onto the seat by the third law. Okay, now if you notice, if you're not moving, v is 0, the normal force is just equal to mg. But if you're moving, the normal force is less. This is the situation where you kind of feel like you're coming out of your seat, right, if you go over a bump. The opposite occurs when you go through a dip. Okay, so this is the one I gave you for the practice test. For the actual test, make sure that you can do the one where you go through the dip in the road. Okay, I don't want to say too much about that. Okay, excellent. So put the numbers in. We have everything to solve it there. Okay, here's the next one. This is sort of mostly Chapter 7, but a little bit of Chapter 6 idea. A scooter has wheels with diameter 120 millimeters. Okay, so that's perfectly good. That's the diameter. And millimeter is perfectly good unit, just not SI units. So remember, the radius would be half that. So 60 millimeters. And then let's put it into SI units. Divide by 1,000. 1, 2, 3. So 0.060 meters. Okay, good. What is the angular speed? So remember what angular speed is. That's omega. How much is omega? You know, SI unit of omega is radians per second. Okay, they're actually, if you look at these answers down here, this is revolutions per minute. So really what they're asking for is, what is the frequency? Could have been worded a little bit better. So usually angular speed, that's what omega is, measured in radians per second. They're actually asking for the frequency. That's what RPMs are, revolutions per minute. Okay, when the scooter is moving forward with a speed of 6 meters per second. Okay, so we know the relationship between tangential speed, that's what this is called, our regular old speed that we had before, and angular speed. So V is equal to omega times R, and then we also know omega is equal to 2 pi f. So if we want, we can put that in here for omega. So let me do that. 2 pi f times R. Okay. So good. The only thing that we don't know then is the frequency, and we can solve for it here. Be careful. This is revolutions per minute. The way that we're doing this now looks like it's going to come out to be revolutions per second. Then we'll have to convert it to revolutions per minute. Okay, let's actually put the numbers in for this one. So V divided by 2 pi R turns out to be F. Okay, so we've got 6 meters per second divided by 2 times pi times the radius, 0.06 meters. And you see it comes out in per seconds. Okay, let me grab my calculator. So 6 divided by 2 would be 3, so then I still got 3 divided by pi. 0.955, and that's per second. I need it to be per minute, so 0.995, or sorry, 955 per second. That's a decimal point. 60 seconds for 1 minute. And that'll give you the amount of revolutions per 1 minute. Pretty close to 60, but let's see. 0.955 times 60, 57 or so. Now, you might ask, where's the revolutions at? Why didn't that come out in the unit? So, a revolution is just, it's not really a unit, it's just describing what's going on. Okay? So, let's see if there's one that's close to this. Probably, okay, nothing's really close enough, I would say. Let's see if we made a mistake here somewhere. 6 divided by 2 would be 3 divided by pi. Ah, I forgot the 0.06 here, so that's not correct. So I should have had 3 divided by pi, which I did. That's where I got 0.955, but I forgot to do the divided by 0.06. This would be about 16 per second. And then 16 per second. Same thing over here, 60 seconds per minute. Scoot this up a little. So times 60. 955 or so. So that would be revolutions per minute then. Okay, that's better. It's always nice to see the answers on there when you work out the problems, isn't it? Okay, so a little forgetting of this 0.06, but we recovered. All right, let's look at the next one. Uniform solid cylinder. Before we do that, this was a circular motion problem. Now, if you notice from the practice test, I did not put any Newton's universal gravitational force question on here. That comes from this. I did not put this on the practice test. It's not going to be on the actual test. So we did some homework questions about like the International Space Station going around the Earth, that sort of thing. I didn't put any circular motion problems with with Newton's gravity and satellite motion on the test. Okay, narrows down what you have to study a little bit. Okay, here's the next one. A uniform solid cylinder, mass 10 kilograms, can rotate about a frictionless axle through the center as shown in this picture. A rope is wrapped around the outer radius over here, and that is 1 meter, and we know that this force is 5 newtons. This force is 6 newtons. Okay, and then this is 1 meter, and this is a half of a meter. Okay, so this is a chapter 7 question, right? This is a force acting at a distance. We have a torque. So the rotational world is just always a little bit more complicated, because not only do we have a force, it's important where it's acting on the body to get something to rotate. Okay, and here's the shape of it. They say it's a solid cylinder, so you have to look up the moment of inertia of a solid cylinder. So 1/2 mr squared. That's the rotational inertia of that shape. You know, it's a solid cylinder, so it's 1/2 mr squared. If this were a hoop with all the mass on the outside, it would just be mr squared. There's a nice table in the chapter that has all the moments of inertia broken down. And then what do we ask for? What is the rotational inertia? That's what, or sorry, what is the angular acceleration? Okay, so we've got Newton's second law for rotation. So the net torque is I times alpha. Just like the net force was m times a, the net torque is I times alpha. And then here we've got to supply the information. Okay, so this force would make it rotate counterclockwise. This force would make it rotate clockwise. Okay, so just like we did before with Newton's second law, torque I alpha, put in the actual torques. I'm going to call this one torque 2, which is it comes from F2 minus torque 1. Okay, so then I have I alpha. Now torque 2 would be F2 times R2 minus F1 times R1. So again, it looks like Newton's second law, right? It's more complicated. Where is the force being applied? And the force and this lever arm are perpendicular to each other. So I would have, you know, the sine of 90 if you look at the formula, which turns out to be 1. So I didn't write that part here with the torques. Okay. So then alpha turns out to be F2 over R2 minus F1 over R1 divided by the moment of inertia. Again, the rotational world is just a little more complicated. In the good old days of F is equal to ma, this would just be m. But in the rotational world, it's I, so you actually have to calculate what I would be. So 1/2 the mass, which is 10 kilograms, and then the radius of the shape. Well, that turns out to be 1 meter. It's the same thing as R1 here. Well, luckily this is mathematically not too hard to solve. 1 squared is 1. This turns out to be 5 kilogram meters squared. Okay, that's what I is equal to. Okay, so let's actually put the numbers in and see what we get here. So this would be 6 newtons acting at 1/2 of a meter minus 5 newtons. Sorry, 6 newtons, yeah, 1/2 meter. 5 newtons acting at 1 meter, and then divided by what I just got here, 5 kilogram meters squared. Okay, so this would be like 3 minus 5, so that would be 2, actually negative 2 on the top. So 2 over 5 would be 0.4. Technically, this comes out to be minus 0.4 radians per second squared. Okay, you'll have to work out the units, but you can do that. A newton is a kilogram meter per second squared. You'll see that the kilograms and the meters squared cancels out, and you're left with just seconds squared on the bottom. Okay, so really this should have said, what is the magnitude of the angular acceleration? And should be 0.4. Let's see if that's correct. Okay, go to the last page for the answers here. So number 3, choice C. Okay, good. All right, good. So there will be a torque problem, and probably involving, a Newton's second law for torque. This one is sort of the full version of it, where you actually have to calculate I. You actually have to calculate torques. So take a look at the homework that goes along with that, which I believe is homework 8. Okay, good. A rotating system shown in the figure differs only in 2 identical movable masses. Okay, so these masses are on the outside compared to these. These are closer to the inside. Okay, so positioned at distance r from the axis on the left, so this is distance r. This is r over 2 here. If you release the hanging block simultaneously from rest and call TL the time taken from the left, and TL is the time taken by the right, T right, okay? To reach the bottom, respectively, then which one is greater? Which one takes longer to hit the ground? Okay, so we could answer this in terms of moment of inertia. So the moment of inertia of the left, I'll do it down here, is greater than the moment of inertia from the right. Why is that? I would say because in the left side, we have the masses at a greater distance from the axis of rotation. I'll just abbreviate that, than the right side. And then something over here maybe like, so therefore the left side is harder to rotate and takes more time, and the block takes more time to hit the ground. Something like that. Just remember what moment of inertia is. It's really a measure of how hard something is to rotate. So although same amount of mass here, same amount of mass here, when you have more mass to the outside, it's more difficult to rotate. So maybe I would say it like that, actually. The left picture has more mass away from the axis of rotation, so it's more difficult to rotate. Therefore, the right side, which has a lesser moment of inertia, this side would take longer to hit the ground than this side. This side's more difficult to rotate. Something along those lines. So you have a question on this idea of moment of inertia and what it actually represents. Okay? So, say you had this situation. Or you had this situation. So this situation is, you're going to grab this in the center and try to get it to rotate. Here you put the mass right in the center and try to get this one to rotate. Even though the mass is the same, if you grab this in the center and try to get it to rotate, it's much more difficult than if you grab this one and try to get it to rotate. Okay. All right, let's look at the next one. I use a program that randomizes the order of the questions, but it looks like we've got a lot of chapter 6 and 7 right here in the beginning. So let's see what else is coming up then. A 2-kilogram mass moving at 5 meters per second suddenly collides head-on with a 3-kilogram mass at rest. If the collision is perfectly inelastic, okay, we know from the lab that means sticks together. What is the speed of the masses just after the collision? Okay, so you'll definitely have a sticks together type collision. Why don't I call this one like mass 1, mass 2, and then over here they stick together. So this is the initial situation. This is the final situation. So V2 initial is 0 because it's at rest. V1 initial is 5 meters per second. And we know this one's 2 kilograms, and this one is 3 kilograms. And then afterwards they stick together. What is the speed of the combination right after the collision? Okay, so the initial momentum of the system, that means before the collision, is equal to the final momentum of the system, that means after the collision. So the initial momentum of the system is just m1 v1 initial. Mass 2 is not moving, so I'm not even going to write m2 v2 initial, it's just 0. And then this would be m1 plus m2, because they're stuck together, times their common final speed. Okay, so then you have m1 v1 initial divided by m1 plus m2, common final speed. So we would have 2 kilograms times 5 meters per second divided by their total combined mass, 2 kilograms plus 3 kilograms. So 2 meters per second. Okay, very good. It's got to be less than 5, right? Because they're sticking together. Okay, excellent. So there's a sticks together type collision one. Definitely going to be on the practice test as well. 3 objects are moving along a straight line as shown. Take the positive direction to be to the right. What's the total momentum? Okay, so remember momentum again, mass times velocity. Let's just go through these. So we've got 8 kilograms moving at 5 meters per second, minus, because this one's going to the left, 15 kilograms, 4 meters per second. Really, it's the 4 that's negative. I could do plus and then put the minus sign there. Same idea, though. And then this one's moving to the right, 3 kilograms, and then 2 meters per second. So 40 minus 60 plus 6. So we've got minus 14 kilogram meters per second. Okay, good. So the net momentum of the system is to the left. There's the negative side. Okay, good. So all the ones on the actual test will be multiple choice. I just didn't have a chance to figure out some multiple choice questions for this one. Okay, the idea is still good, though. We're looking at kinetic energy and spring potential energy. As shown in this picture, a 4 kilogram block, I'll just call this mass, is moving at 5 meters per second. So the speed of this is 5 meters per second. It says it right there too. Okay, a horizontal frictionless surface towards an ideal spring that's connected to the wall. After the block collides with the spring is compressed a maximum distance of 0.68 meters. So that's how much the spring is compressed. What is the speed of the block when the spring is compressed by only half of the maximum distance? Okay, so what's the speed? Maybe I should call this like x1 or something like that. I'll call this one v1 just to distinguish it. What is the speed when we have x2? And x2 is half this, so 0.34 meters. Okay, so the idea here is we're taking kinetic energy and turning it into spring potential energy. Now in the first part, all of the kinetic energy becomes spring potential energy. So all of the kinetic energy becomes spring potential energy when it's compressed the most it can be. So this would be 1/2 mv1 squared is equal to 1/2 kx1 squared. Now they tell you what x1 is, and we know what v1 is, we know the mass, so we can use the spring constant. We could use this formula to figure out the spring constant. So that's kind of the first part. The second part is we're taking kinetic energy. Maybe I'll call this the initial amount of kinetic energy. And we are only compressing the spring by half as much. So we still are going to have some spring kinetic energy, or sorry, some kinetic energy. Actually, I might call that 2, and this one 1. Okay, yeah, that's better. Kinetic energy 1 that we started with is going to be turning into spring potential energy, but we still have some kinetic energy left over. Hopefully that makes some sense. Let me regroup and go through it again. So the first part, we're taking all of the kinetic energy and turning it into spring potential energy. I'll put a little 1 there. Okay, so all the kinetic energy becomes spring potential energy. We can use that to figure out the spring constant. Now the second part is, what is the speed of the block when the spring is compressed by 1/2 the maximum distance? So what is the speed when it's only compressed by half as much, so 0.34 meters? You might just guess like, okay, well, it's half as much, so it's going to be moving half as fast. We don't really know if that's true or not, right? Because the spring potential energy is 1/2 kx squared. So it's probably, maybe it's a direct relationship, maybe it's not. We don't know that for sure. And if you can see that, it's not, because we've got this squared here. Okay, so let's first get the spring constant. I'll do that right here, I guess. So the 1/2s cancel out, and just to save a little bit of space, mv1 squared over x1 squared is equal to the spring constant. So you'll have to get the spring constant that way. Let's actually do this. So we got 4 kilograms, 5 meters per second, don't forget to square it, divided by how much it's compressed, 0.68 meters. And again, don't forget to square it. Okay, make sure I did this right. The 1/2s cancel out. We got mv1 squared over x1. That is going to be the spring constant. Mass 4 kilograms, moving at 5 meters per second, and that's when it's completely compressed. Okay. So we've got 4 times 25, that would be 5 squared, divided by 0.68 squared. So about 216 or so newtons per meter. That's the spring constant. Okay? And now we can figure out over here. We've got the spring constant that we needed. We'll have 1/2 mv1 squared, turns it out to be 1/2 mv2 squared plus 1/2 kx2 squared. You have to do a little bit of work here, not too bad though. The only thing that you don't know now is v2. So there's a 1/2 in everything, so the 1/2 goes away. Then the only thing that you have to do, several steps of algebra, but you can figure out v2. So I'll put dot, dot, dot. Take a look through here, solve for v2, right? You know this, you know the mass, spring constant we just figured out, and we know x2. Okay, so I'll leave it at that. That's from chapter 10, Conservation of Energy. Okay. Good, so yeah, kinetic energy, just as a little reminder, 1/2 mv squared, spring potential energy, 1/2 kx squared. Okay, number 8 here, a block of mass m, that's this one, 5.6 kilograms, moving along a frictionless surface with a speed of 6.5 to the right, collides with this bigger mass at rest. Okay. After the collision, the 5.6 block recoils with a speed of 0.7 to the left. What is the speed of mass m after the collision? Okay, so this guy's not moving, this one's moving, they collide. What's the speed of this one after the collision? Okay, so whenever you see a collision, use conservation of momentum. Now these don't stick together, so you can't do the same thing that we did before. This part is the same. And let's put in the details here. So m times v initial, right? That's the only one that's moving. This one's not moving. I could put big M times whatever this v is, but the v is 0, so that part would be 0 anyway. And then afterwards we have m v final plus big M times v. And they're not stuck together, so this is not a common velocity that they have. Now what we're trying to figure out is this. Everything else is written here. Usually I would write this stuff out like little m 5.6, v initial 6.5. V final, be careful, negative 0.7 because it's moving to the left. Big M, 11.2. Okay, and what we're trying to figure out is big V, the speed of the big mass after the collision. Okay, we'll have to do a little bit of algebra here. M V initial minus M V final is equal to big M times V. So M V initial minus M V final divided by the big mass is equal to V. Let's put some numbers in here. M, 5.6. Moving at 6.5 minus 5.6, and then times V final, which is minus 0.7, so be careful with that. The whole thing divided by 11.2. All right, let's see what we get. 5.6 times 6.5. Minus minus, so you can leave it minus minus if you want, but I know that that would become plus. 5.6 times 0.7 divided by 11.2. So 3.6 meters per second. Okay, good. Let's choice C here. All right, very good. Excellent. Make sure that that's the same thing. I'm sure it is. It'd be kind of a choice C, yeah. Miraculous if it came out to be something different. Okay. You know, just because, what are the odds of just randomly getting the correct answer? Okay, well, it happens, though. Anyway, back to this problem. This is also from Chapter 9. A 0.14 mass baseball. Kilograms rather. This is traveling initially at 27.1 meters per second, struck by a bat with an average force, okay, force of 5,000 newtons, which results in a velocity of 37 in the opposite direction. Okay, so it's important to include that fact. That's why I put minus 37. How long were the bat and ball in contact? So if you notice, mass, velocity, force, and time. This is a candidate for the impulse relationship. Impulse, just another word for change in momentum. Force times time, mv final minus mv initial. That's basically the ways to write it. Okay, final momentum minus initial momentum. Okay, so that's the impulse relationship. All these other parts are equal to each other. Really, I should put a little vector sign above all these just to remind us that if it's going to the right, it's positive. If it's going to the left, it's negative. That's all that the vector sign means there. Right is different than left also. Okay, so the part that we could use is this part. Force times time, mv final minus mv initial. Okay, so we are given the mass, the final velocity, the initial velocity, and we just want to figure out the amount of time. So mv final minus mv initial over the force. Okay, so when you put the numbers in, we have everything for this actually. So now one thing that you'll notice when you do this, unless you specifically say that this force is negative, this time will come out to be negative. So really, this should be 5,000 newtons. If I say the ball is initially moving this way, later on it's moving this way, what would the direction of the force have to be? Well, the force would also have to be this way. Okay, so yeah, technically negative for the force. Okay, very good. So there will be an impulse relationship like this. Now let's look at the next one. 10,000 kilogram car experiences a force of 9,500 newtons, slowing down from initially 30 meters per second down to a speed of 15.9 meters per second. How far does the car travel? Okay, So this problem has mass, velocity, force, and displacement. This is a great candidate for the work-energy theorem. So work, F times delta x. Technically there's a cosine of theta part here, but these are the force and this are anti-parallel to each other, so that's the cosine of 180, which would just actually give you a -1. I'll put that in there just to be complete. So work, force times displacement, what does that give you? The change in kinetic energy. So kinetic energy final minus kinetic energy initial, 1/2 mv final squared minus 1/2 mv initial squared. Okay, good. So just like this problem, force, time, mass, and velocity, this is force, mass, displacement, and velocity. So, depending on what you're given, you'll have to figure out which way to do these problems. Okay, now let me just say one thing about number 9 again. You're given the velocity and the time. If you wanted to, you could figure out the acceleration. Once you have the acceleration and the net force, you could figure out oh, you don't have the time actually, so maybe you can't quite do it that easily. But you do have the mass and the force, so you could figure out the acceleration for this part, and then knowing the acceleration, the final speed, and the initial speed, you could work backwards and get the time. The point of the impulse relationship is to make it simpler for us, so we don't have to look at it as two different kind of problems. Same thing here. You know the force and the mass. You could figure out the acceleration, and then you've got the final speed, the initial speed. You could use kinematics then to figure out the displacement. Okay, anyway, so back to this then. So F delta x. Now we're assuming that this force is slowing us down, right? Normal force, mg. This force is slowing us down. So F delta x cosine of theta. If you're moving this way, and the force is back the other way, the work is technically negative. Or cosine of 180, -1, it's the same thing. So if you wanted to put cosine of 180, that's where the minus sign comes from. I just know I'm moving one way, the force is back the other way, because it's slowing me down. That's where the negative sign comes from. Okay, and then the part I could use here is 1/2 mv final squared minus 1/2 mv initial squared. Okay, then the only thing that you don't have is the delta x that you're looking for. So how did I know to use this equation? Well, the clue is, based on what I'm given, I could use the work-energy theorem. Same thing up here, based on what I'm given, I use the impulse relationship. Okay, so then delta x turns out to be 1/2 mv final squared minus 1/2 mv initial squared over minus f. Okay, so put the numbers in, we have everything for that one. Okay, just a couple more to go here. When an object is in uniform circular motion, the direction of the acceleration is. Okay, so uniform circular motion means at a constant speed. Whenever you're going in a circle, you have to have, especially uniform circular motion, you have to have a force towards the center, or you wouldn't be going in a circle anymore. So for example, here's a mass on the end of a string. This is going in a horizontal circle. The force that's towards the center is tension in this case. If you cut the rope, there's no more force towards the center. This just goes flying off the way that it was normally going. Okay, so the direction of the acceleration, always directed towards the center. Directed away from the center, no. The same direction as the velocity, nope, that would only be if it was speeding up that you would have a part that way. Opposite direction of the velocity, depends on the speed. The direction doesn't depend on the speed. Directed towards the center of the path, yeah. So you could just, do a picture like this and just say there must be a force towards the center, therefore there has to be an acceleration towards the center because you have a force towards the center. Okay, so you'll see something similar to that. Okay, finally, another one. This is a conservation of energy one as well. A bead is moving with the speed of 20 meters per second at position A. Okay, so velocity A, 20 meters per second, and you know the height here. I'll just call this height A. The track is friction-free and there is no air resistance. What's the speed at C? Okay, and then here's the height at C. So the beauty of conservation of mechanical energy is, if you know the total energy here, it's equal to the total energy here. You don't have to worry about what goes on in between. You could do this problem with forces, try to use gravity, but gravity's changing. The component of gravity where this is moving is changing direction because the angle is changing direction. You could do it like that. You'd have to use calculus. Or we could just say that the mechanical energy at A is equal to the mechanical energy at C. And then we don't really care what happens on that part. Okay? So energy conservation. This would be the kinetic energy at A plus the gravitational potential energy at A equal to the kinetic energy at B plus the gravitational potential energy. Oh, sorry. This is C, not B. C at C. Okay. Yeah, that looks bad. Kinetic energy at A plus gravitational potential energy at A, kinetic energy at C, and then the gravitational potential energy at C. Okay, then I can put in the details here. Now, look, they don't give you the mass, but don't worry. If anything's ever going to cancel out, it's the mass, right? We've learned that already. 1/2 mv_a squared plus mgh a, height A, is equal to 1/2 mvc squared plus mg height at C. And then there's a mass and everything, so the mass cancels out. Dot, dot, dot. The only thing that you don't know is the velocity at C. Dot, dot, dot means, do the algebra here. Okay, so remember, gravitational potential energy is mgh. Or sometimes maybe you've seen it written as mgy. Okay? Excellent. So again, it's over. The test is over 9, 10, 6, and 7. The place to start studying is definitely this practice test, and then go back through the homeworks and kind of fill in some details there. Hopefully, I've given you a little bit of a roadmap here. If you can do all these problems, I think you'll have no problem with the actual test. Just like the first one, you don't get the exact same problems with different numbers. They're similar types of problems. Okay, any questions, just send me an email and I'll talk to you soon. Bye-bye.